Hello and welcome. My name is Konstantina Berta and I'm a researcher at Marine Traffic. Today I will talk to you about a framework for online distributed maritime event detection and forecasting over big vessel tracking data. This work is a joint effort with colleagues from Marine Traffic and CSR Athena Research Center and RapidMiner, and is carried out and funded in the context of the European project IN4. This is an outline of my presentation. First, I will share some background on the maritime domain. Then I will talk about some well-known challenges that are common in the maritime industry, especially in applications that heavily rely on vessel tracking data, such as marine traffic. Then I will present the problem and the proposed solution, describing some of its core components, and last I will conclude the presentation. First of all, let me share some background regarding maritime situational awareness. The framework that we propose meets the requirements of an industrial use case that is led by Marine Traffic and has been implemented in collaboration with our partners to meet the needs of our users. Marine Traffic is a world's leading platform for offering vessel tracking services and actionable maritime intelligence based on the Automatic Identification System (AIS). At any given time, Marine Traffic is tracking over 200,000 vessels each time. So, speaking of our users, this is a typical day at Marine Traffic where 70 GB of data are ingested from AI stations every day and are processed in order to serve approximately 1 million users. The maritime situational awareness is the capability of understanding events, circumstances, and activities impacting the maritime environment. The maritime situational awareness is essential for the preparation, the prevention, and the potential required reaction to provide a sustainable stability environment. Marine Traffic heavily relies on the Automatic Identification System. The AIS is a collaborative self-reporting system that allows marine vessels to broadcast their information to nearby vessels and on ground-based stations. It relies on VHF communication, and although it was initially developed to prevent collisions between vessels, it proved to be a valuable source for improving MSA. Now let's see the main challenges that currently exist in the maritime domain. First of all, the main challenge is the large, rapidly increasing size of data. Secondly, the heterogeneous sources of maritime data. Thirdly, the maritime data often contain redundant, noisy, erroneous information that needs to be cleaned and curated. Next, the vessel tracking data are characterized by their streaming fashion. Last, apart from collecting, curating, and publishing the data in a meaningful way, we need to derive actionable knowledge from it in order to increase the value of input data. We now describe the industrial requirements of a data scientist working at a maritime intelligence company. First, we need to create and deploy adaptive, scalable workflows using big data technologies transparently. And we also need to integrate data science components easily, as for example, components for maritime event detection and forecasting. The need for implementing scalable workflows is crucial, since we need to produce results over large streams of vessel tracking data in real time. We also need to target another broad category of users, which are the end users of an MSA application. These users might be vessel traffic services officers, coast guard authorities, navies, etc. These users need to track vessels in real time in their day-to-day jobs, and most importantly, they need to derive actionable information from its data. For example, the early detection and forecasting of vessel events is crucial in order to take informed decisions and take timely actions. So we need to create a novel maritime situational awareness application that supports detection and forecasting of maritime events, that is scalable and produces results in real time, that uses streams of big vessel tracking data, and at the same time addresses the aforementioned challenges and meets the end user's requirements. To do this, first, we enable the creation of synopses over vessel tracking data. We use the synopsis data engine that creates summaries of streaming data, allows rapid analytics of large data streams with predefined accuracy guarantees, and thus boosts the scalability of MSA workflows. It is publicly available as open source project, and it is developed as a SD as a service on clusters, serving requests for maintaining new synopses on the fly. It enables users to perform continuous queries over streaming data, and it has been implemented as a general-purpose engine that supports a variety of data summarization techniques. It contains a lot of techniques in its library, and we use one of them, the SD sampler for the maritime use case. The SD sampler simplifies vessel trajectories by keeping only the important positions. This means that for each vessel, new incoming vessel positions that do not involve significant changes from previous ones in any navigational parameters, such as location, heading, course, or direction over time, are excluded from the trajectory sample. In this experiment, we compared our SD as a service design to non-SD as a service approaches, using the SD sampler data synopsis that we use for marine traffic data. We executed an experiment over a cluster of 40 CPUs, and we started maintaining 2 SD sampler synopses, and then we started monitoring more vessels up to 10,000 without stopping the already running synopsis. So this figure shows the sum of throughputs for all running jobs for both implementations. The results of this experiment indicate that non-SD as a service does not allow on-the-fly requests to running jobs for maintaining new synopses. Hence, it seems that non-SD as a service cannot maintain more than 40 synopses. SD as a service, on the other hand, has no such limit, since it initiates new tasks to a single running service at a time without downtime. Moving on to the maritime event detection. First, let us explain what we mean with the term simple events. The simple events are building block events and can serve as the basis to more complex event detection operators. Usually, they require computationally demanding operations. Other times, they are not. So, for example, we have events about turn, acceleration, route deviation, events that are triggered when a vessel navigates through shallow waters, proximity events when vessels are very close together, and most importantly, we have eyes-off events that is triggered when a vessel goes out of AIS coverage or intentionally switches off its transponder. How we detect these events? We use a real-time layer, and here in marine traffic at the batch layer, we take as input vessel tracking data as Kafka streams, and we process them in a distributed way using the ACA system. And when needed, for some events, we need to combine them with historical information, so we have a batch layer, and we are able to combine them in a distributed way and derive the aforementioned events. Now over to complex event detection and forecasting. We use an integrated version of the open source tool Wayget, which employs symbolic automata as computational model for pattern detection. It also uses Markov models for deriving a probabilistic description of the symbolic automation and gets as input a set of patterns and a set of input events. For forecasting, it predicts when a pattern is expected to occur. We provide an example definition for illegal fishing. It is often the case that vessels engaged in illegal fishing or other illegal activities switch off their AIS transponders in order not to be tracked. Therefore, using the definition provided in this slide enables us to detect behavioral patterns of fishing vessels when they have their AIS equipment switched off and their speed is within the typical speed range of vessels while they are actually fishing. Now that we have explained most of the core components of our workflow, we are ready to explain how easily we are able to integrate them together. We use a well-known data science platform, RapidMiner Studio, that has been extended by our RapidMiner colleagues to enable users graphically design and execute data science workflows over streaming big data platforms such as Apache Flink and other platforms like Apache Spark and ACA without the need to write custom code. Now that we are able to run our data science workflows, we are ready to visualize the results. So we have developed a visualization component that is essentially a web-based application with a user-friendly user interface that displays the current state of positions of vessels on the map with marine traffic data. We also visualize the simple events that have been detected by the maritime event detector, the complex forecast events produced by the complex event forecasting component, and also some arbitrary information like the past accessed past events. In future work, we will extend even more our framework by connecting it with AUV mission software, and we will apply the extended workflow in the context of a real sea-trial experiment that we will execute beginning of next year in the premises of our partners NATO CMRE. Thank you very much for your attention.